Earlier, we stated that when a magnet is cut in half, and those pieces are cut in half, and this is continued all the way down to the atomic level, each piece would still have a north and a south pole. So we'll do the first cut here. We cut it in half. This piece has a north and a south pole, and this piece has a north and a south pole. The real explanation of this requires an understanding of quantum mechanics, but we can still use some classical physics concepts to give you a working understanding of why this happens. Classically, the Bohr model of the atom shows electrons orbiting the nucleus. What is current but a bunch of moving charges? So we can say that due to these moving electrons, they're a current, they will generate a magnetic field. This is down at the atomic level. Now, of course, it's not that simple, but if you've already had chemistry, you know that electrons pair up kind of like in opposite directions there. So most of these magnetic fields generated by the electron movements cancel out. However, for atoms that are midway between shell closures, and we'll learn more about that in quantum, or you may already have had it in chemistry, there are more unpaired electrons, and there will be a net magnetic field from these unpaired electrons. Another contribution to the magnetic field of an atom is a thing called electron spin. Since the electron is a point particle, it really isn't spinning at all. This is an effect explained by quantum electrodynamics, and it's just a cool phrase. This spin factor also adds to the strength of the magnetic field created by the orbital motion of the electrons. So every atom, and this is really the key point, is acting as a magnet with a north and a south pole. We have a name for this north pole of the atom. The magnetic moment, also known as the magnetic dipole moment of a magnet or an atom or electron, is pointed in the direction of the north pole of the object, and that represents the strength of the magnetic field. And the letter for that is mu. It is a measure of how strongly it will interact with an external magnetic field. Using the Bohr model again, where we can talk about electrons moving clockwise or counterclockwise, if we have a current going in this direction, well, that will give us the magnetic moment pointed up. But what's really happening are electrons are moving in the opposite direction, so the angular momentum, this is from last semester, is pointing down. And again, mu represents the direction and strength of the magnetic moment. Let's go up another level in size. The pictures here, they represent atoms and their magnetic fields or magnetic moments, with the arrowhead the north pole and the other end the south pole. So here's a group of atoms whose north poles are all pointed in the same direction. Here's another group. Here's another group. What we call each group of like-pointed atoms is a magnetic domain. In a magnetic domain, each atom has its magnetic moment in the same direction. What do you think's happening below? Which picture could be a permanent magnet? Which could be a piece of plastic? See how we're moving from this over to here, and it looks like a couple of these magnetic domains all lined up. They join together, and then over here they're all pointing in the same direction. So think about that for a sec before you go to the next page. For a random group of atoms, there's no real reason for the magnetic poles to align. The picture on the left shows a pretty random ordering of magnetic field directions, with aligned fields only in each magnetic domain. Looking at the left picture as a whole, the various magnetic fields are going to cancel out, so it would not be a very good magnet in this state. It could be a piece of plastic, or a certain type of metal that could become a magnet with the application of an external magnetic field. And that kind of looks like what's going on here. If you have a certain type of material, it doesn't work for all of them. You apply an external magnetic field, you get everybody to line up. As you move from left to right, more of the magnetic field lines are in the same direction. The middle picture here shows a pretty large domain where all the field arrows are pointed up. Finally, in the third picture, all of the field lines point up, and remember, they point in the direction of the North Pole, and this would be the south. And you could visualize this as a bar magnet with the North Pole facing up.